Hello everyone, I'm Mr. McBrien. This is SCH3U, Limiting Reagents and Percent Yield. The Ontario curriculum specifies that students will solve problems related to quantities and chemical reactions by performing calculations involving percentage yield and limiting reagents. This is what we'll do today. So in class today we'll do a little group activity, making methane from molecule kits. In lieu of that, we're going to look at building cheeseburgers instead. We're going to use this as an example to define the limiting reactant or limiting reagent. And then we're going to use some of our new stoichiometry skills to determine the limiting reagent, given amounts of each reagent, and calculate the percent yield, given an amount of a product. Okay, so what's a limiting reagent? Well, if we're working to make something in the kitchen, cooks follow a recipe when they're making a new dish. And when they want to cook something, they need to know the amounts for each given ingredient. So if we wanted to make double cheeseburgers, we might say we need 1 bun, 1 tomato slice, 2 slices of cheese, 2 burger patties. Pretty straightforward. If we want to make 5, then we have to multiply those ratios by 5. We need 5 buns, 10 patties, 10 slices of cheese, and 5 tomato slices. Pretty straightforward stuff. Now, the question comes up when we start to look at how many of each given ingredient we have. If we have 1 bun, 2 patties, 2 slices of cheese, and a tomato slice, we obviously can make 1 burger. If we have double that of each one of those, we can make 2 burgers. And if we get wacky and say we have a mole of buns, 2 moles of patties, 2 moles of cheese, and 1 mole of tomato slices, we can make 1 mole of burgers. But here's where things get interesting. What if we have 10 buns, 20 patties, 10 tomato slices, in other words, enough of each of those to make 10 burgers, but we only have 2 slices of cheese? Well, in that case, we can only make 1 burger even though we've got lots of the rest of the ingredients. Okay, so that's the basic concept we have that we're dealing with today. We can't make more than 1 double cheeseburger with those ingredients. The slices of cheese limit the number of cheeseburgers we can make, therefore they're the limiting reagents. And this is that limits the amount of product we can form, and it's a perfect metaphor for the chemist who has a small amount of one reactant and more of another reactant. Okay, so if we take our balanced chemical reaction, we can predict the amount of product formed from the amounts of ingredients available. So let's look at our familiar Haber process. Nitrogen and hydrogen are combined to form ammonium. And we can see that when 1 mole of nitrogen reacts with 3 moles of hydrogen gas, we get 2 moles of ammonium. No big deal. Now, if we had 2 moles of nitrogen and 3 moles of hydrogen, how many moles of ammonium can we make? Well, in theory, based on the nitrogen, we could make 4 moles of ammonium. However, we wouldn't have enough hydrogen to do that. And so we can only make 2 moles rather than 4. So when we look at that, we say that the amount of hydrogen is limiting the amount of ammonia that can be made. It's the limiting reagent. And one thing that's worth noting is that the hydrogen will run out and we'll have leftover nitrogen. And we can say in chemistry terms that nitrogen is in excess. It will be left over when our reaction is complete. And we can even calculate how much will be left over. We could, in many cases, do this by examination, or at least in this case, we could do it by examination. Usually we'd have to do a calculation. So we know that we can only react 1 mole of nitrogen to react the 3 moles of hydrogen. And that means we have 1 mole left over because, again, we started with 2 moles of nitrogen. So we can deal with 3 kinds of questions associated with limiting reagent. And it's worth looking at these with a little bit of detail, because basically this is half the point of this chemistry unit. So the first thing we can do is determine the limiting reactant, which one of the reactants will run out first. The next thing we can do is determine the amount of product we will have, theoretically. And the third thing we can do is determine how much excess reactant is wasted. Okay, so let's go through some examples. If we react copper with sulfur to make copper sulfide, the balanced equation is given here. If we have 82 grams of copper and react it with 25 grams of sulfur, which one's the limiting reactant? Then we can ask ourselves the second part, what's the maximum amount of copper sulfide that can be formed? And finally, once we know which one's the limiting reactant, let's find out how much of the other reactant will be wasted. Okay, so our first goal, calculate how much sulfur would react if all of the copper were reacted. And I encourage you to take this approach every time. It's very straightforward and it's very hard to get it wrong. From that we'll determine the limiting reactant, and then we'll use that to calculate the amount of product formed and the amount of excess reactant left over. So, the question we should ask ourselves at the start of every one of these questions, we redefine the question to be, if all of the first component reacted, how much of the other component would I need? And when we do this, we distill down the problem to a very simple definition. So what we can say is, how much sulfur do I need to react with 82 grams of copper? And then, as we learned yesterday, we apply first our definitions of molar mass, then a stoichiometry term, 2 moles of copper, 1 mole of sulfur, and then finally we move ourselves back into the mass domain by multiplying by the molar mass of sulfur. And when we're finished crunching this through the calculator, we find out that in order to react all 82 grams of copper, we would need 20.7 grams of sulfur. But remember that we started with 25 grams. So, simple logic tells us that sulfur is in excess. We're going to run out of the copper, and we're going to have 25 minus 20.7 is 4.3 grams of sulfur left over. So 2 parts of the question are already complete. So then the last part of the question is just to say, now that we know our limiting reagent, how much product will be produced? And so what we do is we say 82 grams of copper. Again, move ourselves into the molar domain by dividing by the molar mass of copper. Apply our new stoichiometry term, 2 moles of copper for 1 mole of copper sulfide. And then move ourselves into the mass domain by multiplying by the molar mass of copper sulfide. And the answer is that we should get 103 grams of copper sulfide. And so we can draw our inferences from there. The reaction between 82 grams of copper and 25 grams of sulfur can only produce 103 grams of copper sulfide. The copper will run out, and we'll have 4.3 grams of the sulfur left over. Now let's try a second example. Let's react hydrochloric acid with magnesium metal to form magnesium chloride and hydrogen gas. So let's imagine our question this time. It's what's the limiting reagent when 6 grams of hydrochloric acid reacts with 5 grams of magnesium? What's the amount of hydrogen that can be formed? And how much of the non-limiting reagent, the one in excess, is wasted? Quick note here. It's a good idea every time you work on one of these questions, just quickly make sure that the equation is balanced and balance it if necessary. So let's do that now. So magnesium is currently balanced, hydrogen is balanced, chlorine is balanced. Good. Okay, we can proceed. So we'll ask ourselves the question again. How much hydrochloric acid will be consumed if we react all 5 grams of magnesium? And now we can apply our standard slingshot calculation, finding the number of moles of magnesium by dividing by the molar mass of magnesium, applying our stoichiometry term, 2:1 hydrochloric acid to magnesium, and then moving back into the mass domain by multiplying by the molar mass of hydrochloric acid. And the answer we come up with is 15 grams of hydrochloric acid. So if we reacted 5 grams of magnesium fully, we would require 15 grams of hydrochloric acid. But remember, we only had 6 grams of hydrochloric acid to begin with. This means hydrochloric acid is our limiting reagent. Now, knowing this, we can use our limiting reagent to do the calculation to find how much hydrogen we will make. Okay, so 6 grams of our limiting reagent. Again, we fire up the slingshot, divide by the molar mass of hydrochloric acid, apply our stoichiometry term. Notice this time it'll be in terms of hydrogen and hydrochloric acid. So it's 1/2. And then move back into the mass domain by multiplying by 2.0, the molar mass of hydrogen gas. And so our answer is that we will produce 0.164 grams of hydrogen. For sake figs, if this were our final expression, we would say 0.16 grams of hydrogen gas. Now, we can also find out how much magnesium we'll consume by, again, firing up the slingshot. We divide by the molar mass to move into the molar domain. Apply our stoichiometry term, this time in terms of magnesium, which has its coefficient of 1, and hydrochloric acid, which has its coefficient of 2. Move back into the mass domain by multiplying by the molar mass of magnesium. And we find out that we're going to consume about 2 grams of magnesium. And then if we want to see how much magnesium will be left over, we simply subtract the mass of magnesium we started with and get 3 grams of magnesium left over. Now, one of the things that chemists like to do is to talk about the efficiency of a given reaction. So let's talk about that now. In theory, when any class takes a given exam, every student should get a grade of 100%. And of course, the majority of students don't get 100% on every exam, and we express their grade to show how well they've done. This is not much different than a percent yield calculation that we do in the lab. What we wind up doing is saying that once we've done our calculation of our theoretical yield, the amount of the product we should get, we can then talk about how much we should get. You'd be tempted to say that if our theoretical yield is 5.2 grams, that we should recover 5.2 grams of the product. But, in fact, that's probably more like the exception than the rule. Okay, so we talk about a theoretical yield. That's the maximum amount of product that could be formed from a given amount of reactants. The amount of product that we collect is what's called the actual yield. And typically, the actual yield is less than the theoretical yield. Not always, but it often is. So we simply express the ratio of the actual yield to the theoretical yield as a percent, and this gives us an idea of the efficiency of the reaction. And we already know how to do those kind of calculations. So the percent yield is just the experimental yield divided by the theoretical yield times 100%. So why would a percent yield be less than 100%? Well, there's lots of reasons. In some cases, reactions don't go to completion. So in this kind of situation, we'll get less of the product than we would expect. So some starting materials will be left over. Now, there are other things that are maybe a bit more complicated to imagine, but we can imagine when our reactants weren't pure when we started with them, then the assumption that we'll get 100% of our product becomes faulty at that point. But in fact, in much of chemistry, what we see are competing reactions where we get some other product as well, and some of our reactants are taken into side reactions. And so this will actually give us a lower yield than the theoretical yield, and some of these things, even worse, give us impure product, which is a bit of a problem. Now, there also can be physical factors. So we can lose product during filtration or transferring between containers. If it's stuck to the side of the container, or some small particles make it through the filter paper, or even when we're rinsing the product, if some is dissolved, we can lose some. Now, probably the most typical situation that gives you more than 100% yield would be solvent caught on the product, causing it to actually give us a higher yield than we'd expect. Okay, so in order to calculate the yield then, let's try an example right from the beginning and walk through it again. So let's take the case of heating calcium oxide in carbon dioxide to get calcium carbonate. So our question on our exam is, what is the theoretical yield of calcium carbonate if 24.8 grams of calcium oxide is heated with 43 grams of carbon dioxide? What's the percent yield if we get 33 grams of calcium carbonate? So whenever we get this question, we have to redefine it slightly. We have to figure out which reactant is limiting and then decide what the theoretical yield is. Okay, so here's our reaction. We're going to find the limiting reactant in our reaction now. And again, we redefine the question to say, if all the calcium oxide reacted, how much CO2 would we need? And when we find the answer to that, the identity of the limiting reactant is trivial to determine. So we can take our 24.8 grams of calcium oxide and move into the molar domain by dividing by the molar mass of calcium oxide. Then we can apply our stoichiometry term. Notice in this case it's 1:1. And finally move ourselves back into the mass domain by multiplying by the molar mass of CO2. And the answer we get is 19.5 grams of CO2, would be consumed if all the calcium oxide reacted. Now, so we have far more than 19.5 grams of CO2, therefore CO2 is in excess and calcium oxide is the limiting reagent. Okay, so knowing that calcium oxide is the limiting reagent, we can fire up the slingshot again and say that for 24.8 grams of calcium oxide, move yourselves into the molar domain first. Apply the stoichiometry term, again 1 to 1. And then move ourselves back into the mass domain by multiplying by the molar mass of calcium carbonate. And we find that we get 44.3 grams of calcium carbonate is our theoretical yield. Okay, so once we have our theoretical yield, we can find the percent yield then by simply using our experimental yield, in this case 33.1 grams, I believe. 33.1 grams of product divided by our theoretical yield times 100% gives us about 75% yield. So, today we talked about the limiting reactant. It's defined as the starting material that will run out first in a given reaction. We talked about the theoretical yield, the amount of product we would get if all the limiting reactant is used up. And we talked about the actual yield and expressing this as a percent to give our percent yield. For our homework, please read section 7.2 in the textbook and do questions 40 to 44, and number 48 should be interesting as well. And please review the lab outline for tomorrow and do the pre-calcs to be prepared to be efficient tomorrow. Thanks very much and have a great night.